All right, here we go. Number 1, the duration of a punch is 3 times longer than normal when a boxer leans back while getting hit. By how much would the force change compared to normal? So the equation we said we're thinking about is this one. Impulse, so force times the time interval, delta t, is equal to change in momentum. So first of all, notice that the momentum change is exactly the same. There's no change to it. Okay? So the amount of momentum change is the same. You're going from 0 to whatever happens to your face, and then back again. So the momentum change is the same. And then it says that the time interval is going to be 3 times larger. So it goes up by 3 times. So then the question is, what do we think is going to happen to the force? Is the force going to be 3 times more force, 3 times less force, 9 times less force, or no change at all? Okay? Let's see. Matthew, what do you think? A, B, C, or D? D. You said D? Why D?
Because there's nothing adding on to the force or taking away from it.
Good. I like it. Matthew, part 2. What's your answer? A, B, C, or D? B. Okay, 3 times less. Why do you think it's 3 times less? Okay, so the time is lengthened. Okay, good. Any other answers? Yep.
I say B as well. I say B as well. But my reason behind it was so it takes 3 times longer to punch in the face, right?
Yep.
So all we know that is less the contact time that he has. So let's just say so B beyond before you pull that region.
Okay. Yeah. Good. So the answer to this one, the correct answer is B. And if you think of the equation over here, so if this is going to have no change, if this is going to be 3 times larger, then this is going to have to decrease by 3 in order to balance out the equation. Think of it this way. If my answer is 10, maybe I do 2 times 5. Let's not do that. Let's do 3. Yeah, let's do 3 and 1. 3 and 1 gives you 3. Okay? If I'm going to make this number 3 times larger, if I'm still going to get an answer of 3, which I am, the momentum change is the same. If I'm still going to get an answer of 3, then this number needs to be 3 times less in order to still get the same answer. So by increasing this by 3, I decreased this by the same amount. And that's to keep the total thing the same. So by that reasoning, number 2, if you cut the duration in half, so if the time is 2 times less, again, we're assuming no change in momentum. That's the same. No momentum change from the momentum change. It's kind of confusing, but then this one should be 2 times more. And if you're having a hard time thinking about that from a math perspective, think about it from this perspective. If you make the force spread out over 3 times of a larger distance, you need 3 times less force because you're doing it for longer. Likewise, if you do the force 2 times shorter, you need 2 times as much force because you're doing it in half the time, right? If you want to do something quicker, you need double the people if you want to do it twice as fast. That's not a perfect analogy, but it's a decent one at least. Good, so 3 times less if you have 3 times longer time, 2 times more if you have half the time. All right, number 3, a karate student wants to break the stack of bricks with their hands. Should they apply their force quickly over a longer period of time? Let's see. Mercy, what do you think? Do you want to do it quickly to hit the bricks, or do you want to do it over a longer period of time?
Quickly.
Why do you want to do it quickly?
Because like the less time, the more impact, I think.
Yes. So the reason you want to do it quickly, and that's a great explanation. Less time, means more impact. And when we say impact, what we mean is force. Okay? So again, thinking about the same equation here, if you're going to have the same momentum change, the momentum change is going to be from the bricks being broken to moving. If you want to make this as large as possible, then this needs to be as short as possible. When karate people do this, they hit and pull their hand off. They don't hit and leave their hand on the bricks. They hit and pull their hands off the bricks. That makes the time of collision very, very, very short, which is going to increase the amount of force that they can apply. All right, bingo. And now we're on the last one. So describe hardness using physics concepts that we've talked about. So when you talk about something is hard and something is soft, what's the difference between them? Indy, what do you think? When you say a desk is hard and a pillow is soft, what's the difference in terms of physics things we've talked about? So let me ask you this. Which one do you think will stop your hand quicker? The desk, the pillow, or do you think they'll stop your hand in the same amount of time? Say again, Indy? So the pillow will stop your hand over a longer period of time. You're exactly right. It'll take longer for the pillow to stop you. And what we've been saying is things that take longer are going to have less force. So something that is hard is going to stop things faster. So your momentum change is going to be equal to a small time interval and therefore a large force. But something that's soft is going to stop it slower. So the momentum change will be caused by a larger time interval and therefore a smaller force. Something that is hard stops things quickly. Something that is soft stops things slowly. Which is why if you jump off of something onto the ground that's hard, you bend your knees when you do it, because that makes the impact longer and therefore makes the force small. Okay, that's the big key with these, is trying to see how they all interact together. Questions on this one? Yep. Go and pull your mask up, Michael. Thanks. Say again?
That was your morning so far.
So far I'm awake. It's a good start. All right.